So hello everybody, I'm Hon Huang. I'm currently an early career researcher at the Centre for Big Data Research in Health at the University of New South Wales. I will be giving you a quick overview of causal inference. So you may have heard of the phrase, association is not causation, when we talk about observational studies. But what does it really mean in terms of causal inference, which concerns the cause and effects questions? So I have this figure from this book, and on the top diamond is the population of interest, and you can see a proportion of it has received a treatment. And denoting A as a treatment and Y as the outcome, when we talk about association, we are actually interested in the subset of population that are treated and untreated, so you have a conditional probability. But when we talk about causal inference, what we are interested in is comparing the effect when all the subjects receive the same treatment. So a popular comparison is the average treatment effect, which compares the expected potential outcome difference between these two groups. And I'll explain this idea of potential outcomes and the superscript notation on Y later on. But of course, the fundamental problem here with causal inference is in real life, subjects only receive one treatment, not both. So not all of the outcomes will be observed. So there are actually three methods or frameworks to perform causal inference. The first one is by Rosenbaum and Rubin, where they talk about the idea of potential outcomes or counterfactual outcomes. So these are outcomes observed if all the subjects are under particular value treatment. So and then that leads to methods such as using propensity score. The second type of method is by Pearl, which uses graphical model, specifically direct cyclical graph, and the do operator to do causal inference. And the last one is by Robbins and Hanan, which they talk about this idea of marginal structure model and emulating target trial. So the emulating a target trial means you set up your observational data in a way that it will mimic a randomized control trial, and from that you perform the causal inference. For the purpose of this talk, I'll use Pearl's graphical model to explain how causal inference can be performed. So I have this diagram from this book, section 3.2, where you have three variables from observation. So this is a DAG for observation, denoted with P. A is the treatment as same as before, Y is the outcome, and X is a special variable called the confounder, which affects the treatment and the outcome. So when we apply the do operator, which is setting a specific treatment value, you get this new modified model denoted P subscript M. Now because you have applied a specific value to A, you now remove the arrow from X to A, because A, the treatment, no longer depends on X. And that's the mathematical notation. Now, I haven't shown you the counterfactuals, but by doing a do operator, you can see how that's the Y there is now a counterfactual for its specific value of A. The key thing here is to notice that although you have two different DAGs, they have some similarity. First of all, the probability of X is the same, and the conditional probability of Y on given A and X are the same in both DAGs. So if we apply Bayes' rule to the left-hand side, and then marginalize out the X, you see that the probability of Y conditional on a specific treatment in the modified graph looks like this. Notice the right-hand side of this equation is the same common properties we talked about earlier. So you can substitute the properties from the left DAG into this equation, and what this also means is that you can get causal estimate from observed data.